Good morning, everyone. It's Richard Young from the School of Engineering, Design and Built Environment, Western Sydney University. And today I'm presenting the topic on applications of non-destructive damage evaluation and structural health monitoring in railway tracks. So our research team in this topic includes Mr. Ralph Zhang, Dr. Helen Wu, and myself. And Ralph is our PhD student and the supervision from Helen and myself. And he's the railway expert working in the transport for New South Wales for quite a while. And his topic for PhD is really focusing on this NDI and SHM in railway tracks. So today we give these contents including the introduction and give the backgrounds, and then we review the major technologies for NDI, SHM of continuous welded real CWRs. And then we give the showcase on the application of these there's three technologies in the CWR in Australia. And after that, we give conclusion and of course open for questions. Okay, so introduction, rail is the most important element of the rail track system, which provides the supporting and the guiding for trains. And between the wheel and the rail had a lot of interactions, and that interaction may generate the failure. So the rail-related railway track failures can be categorized into two major modes. First one is the rail broken. Second one is the track buckling. So in the bottom, you can find the two photos. In the left-hand side, that's really linked to the rail broken mode and initiated from the rail internal flaw or defects. So you can clearly to see the cracks there. And in the right-hand side is the track buckling, misalignment of the continuous welded rails, CWR. And you could find definitely the rails that looks like the noodle and just soft and ended the actual loading. So definitely caused the catastrophic consequences. So in this research, we focus on the track buckling, and that is basically caused by the thermal stresses along the longitudinal direction. So that is really important. We use the NDI and the SHM technologies to measure and monitor the longitudinal thermal stress. And for the three types of the NDE and SHM technologies being used in Australia, and we are not measure the thermal stress directly, but actually we measure the neutral temperature refill, the on-site measurement, and we use the three methods: magnetic, Barkhausen noises method, so mechanical method, vibration method. So in this research, I aim to review these three NDE and SHM technologies, showcase their applications on the neutral temperature infill measurement, identifying their advantage and disadvantage for comparison. And so this is the whole thing. And first of all, we review on NDI and SHM technologies for CWRs, so for all these three methods. So magnetic Barkhausen noise technology actually it adopt the magnetic Barkhausen noise method, and we use the physical parameter obtained from hysteresis loop. So this loop is give the relationship between the field strength and the flow density. And basically this the whole magnetization region from the region 1, region 2, region 3 is of our interest, and especially for the region 3. So the BW1 is a block wall type 1 and 2. So we use actually BW1 and 2 RP between these the magnetization region 3. And we measure the noises, right? And so that's the basically you can see the right-hand side, we can create the calibration curve and link this between these two noise and stress. So we use this ambient and stress relationship and to give the measurement on the neutral temperature. So the neutral temperature is Tn equals to sigma L divided by E alpha and plus T real. So T real is the temperature is under the stress free conditions. So we know the value. And the sigma L is the measurement. And then we know the material property Young's modular E and the thermal coefficient of the real. And then we can determine the neutral temperature of our interest. And the device we used is the track safe release or real scan system, and to measure the longitudinal stress distribution in the CWR track. And it's basically operated by means no contact gauging and allow faster measurement and documentation of actual neutral temperature of the real of interest. So left-hand side, you can find the image, and that is for the track safe release unit, so mounted on the real. And in the right-hand side, this is for the showcase, give one AIS 107LB, this real calibration curve. So you can find the relationship between the stress and the magnetic parameter beta. And for mechanical methods, it used a watch or a frame device, so commercialized for CWR neutral temperature measurement by using equipment of the WERS. And the WERS is technology patented by the Voltok International company. It's based on the beam column bending theories, in which the axial load affects the vertical force required to lift the rail. So here is the equation. So I just don't give the detailed description. And you can see what's the installation of this was equipment. So it definitely lift the track, and then we measured the temperature. So this equipment was designed for measure the neutral temperature with the accuracy of 0.2 Celsius, and with the standard deviation of 1.3 Celsius. This can be used to different kinds of the reals and get instant results of the temperature, neutral temperature by equation. And the last method is the third one, is a vibration method. So it's a de-strengthened, and this strengthened system has the potential of estimating the neutral temperature condition quickly and non-destructively. So basically including the variable speed shaker, tune bar with accelerometer, magnetic real temperature probe, and data acquisition system. So you can see that this motorized the shaker and the tune bar mounted on the rail in the photo below. And for case study on the NDI and the ANSHM CWRS, we do the one by one. Okay, so MBN and also the worst method and also the mechanical method, but we focus on first two. So for the vibration method, it's basically it can be used but with a lot of limitation. And for MBN method, so you can find we really look at the series side the wire of the rail. So on the sharp curves for this case, and we install the real scan probe on the one rail of the sharp curve, and we do the testing and on the mainline track, so over 8 working days, and to measure the neutral temperature. So of course that is got a permission by the Australian Rail Track Corporation, ARTC, and Transport Express Joint Venture, TEGV, and to perform in-track measurements using the real scan and neutral temperature measurement device. So basically it happened before in the North Coast line in Gloucester, New South Wales. And it's just to show some results. So we do have the other comparison. So basically cut the real cut method or cutting real method. very traditionally. We did installation of the string gauge, and for this 4 string gauges on the both up rail and down rail, and do the cutting and look at the measurement. And so in this case, we also use the different equation and considering the displacement in the longitudinal direction and the original length of the rail. So we get the results as well. So compare these 2 methods, and you can find the real scan measurement is more process, and also it's a non-destructive measurement, and they are very close. So some results may have be the variation, but it's still considered reasonable, and you can find the trend is similar, and so it's still pretty much accepted. Yeah. So it's basically one is from the real scan and the other one from calculation. And for mechanical method, and we use the words A-frame. A-frame is simplifying the word system. So here we only talk about this words and system measurement, and also compare with the ambient method as we showed before. So here it happened in the other place on Sydney. It's Broken Hill line, and you can see the both measurement is quoted here. So in the left hand side, as I showed, I just point out actually in the left hand side the figure that's it all Rob is doing the work that the other guys his colleagues. And the results for the neutral temperature measured is pretty close, and except for there's turning point from the mechanical method across the blue line obtained from the real scan, but these 2 methods came very close to the result. The error difference, temperature difference is quite small, so that means that the method is pretty good. And the last one is the vibration method, and definitely is the effective method, have potential to measure the neutral temperature condition quickly and non-destructively. And the shaker contains an eccentric weight which operates over a speed range of 65 to 80 hertz. And after installation, a computer-controlled motor through the narrow sweep encompassing the county level for the bending resonance and records the largest resulting peak-to-peak velocity signal. According to the manufacturer, this velocity signal can be processed and linked related to existing longitudinal load in the rail, and for this either it may be under compression or tension. So this is the method. So you can see the installation of this device on top of the rail and do the measurement, and it definitely can get the either tensile or compressive thermal stress measured. So this is the third method. And as we focus on the first method, so we don't have the data, it's just for the showcase here. And compared to these 3 methods, so what we can find if we look at the equipment accuracy, staff requirement, and track work requirement, limitation of the location, limitation of the environment, productivity, time per measurement, you could find the second method, the strength method, have really good, the performance here. So you can see that with the high accuracy and the precision and the nice preparation, and compared to the first 2, the MBN method and the strength method, the worst method actually is with the high precision, but it need more preparation and labor and time. So that's come to the end of my presentation, give the conclusions. So research finding here, we could say these three methods could be used in Australia, and of course have been used in Australia. And these transit method is the most flexible, efficient method with the least limitation among all three technologies. The worst method provide highest precision, but take much longer time and labor to finish the on-site measurements. The magnetic Hausen noise method sits in the middle with the advantage and the limitation. So future directions, including the developing a systematic NDE and SHM system, which values sensors and equipment, and processing big data use AI technologies, for example, the machine learning, and conducting risk assessment and management, and could help us prioritize the on-site measurement work effectively. So that's all. So would like thank you for your listening. Thank you for your attention. Would like to open for questions.